Okay, hello everybody. Today will be the final lecture of our youth competitive programming series. And today we'll be going over a very essential topic to uh, silver level, at least on this level, a very important algorithm. It's very efficient and fast. It's called binary search. But before we do that, let's go over the homework to yesterday, which was from our prefix sums unit. Okay, so if you guys don't know the problem, I'll just pull it up right now for you guys. So yeah. Okay. So basically you're given a sequence and you want to process a bunch of queries in order. Given L and R, which represents a range to take the sum of, the summation of, you want to print the sum of that range. So this might be a little confusing, just the notation. So let's look at a sample input and see what they're asking us for specifically. So given this range over here of, you can see that they're giving us the bounds of a query, but it's non-inclusive of the last element. So when they're telling us 2, 3, it means, okay, 0, 1, 2. Our first index is 2, and our last index is b minus 1. It's 1 less than the final index they give us because it's non-inclusive. So you want to find the sum from 2 to 2, which is just 100. And that's what they print out here. And then 0 to 3, it's from 0 to 2 as the last index. So 111 it should print out, and that's what it does. 2 to 5, we want to print out the sum from 2 to 4. And that's what it does here. So as you can see, that's what it's doing. We just want to take the sum over an interval. And we could iterate and just add over that interval, but we found a much more efficient way to do this using prefix sums. And using the knowledge we have, we know it would take n time complexity to create the prefix array. And then after that, it would take q queries, and it would be constant for each query. So it's n plus q algorithm. And if we look at our time constraints, we see that n is 500,000 and q is 500,000, meaning that this would run at around like 10 to the sixth, which if we're looking at the USACO limit is much less than what they want. And also, if we take another look at what these inputs tell us, if we did the normal iterative solution, which is n times q, that would take us around like that would probably take us around 2.5 times 10 to the 11th. So that'd be way too much. So you can see we're using an application of prefix sums that allows us to actually solve this problem. Okay, now back to the solution. Okay, so as I said, prefix sum is an n plus q algorithm. So basically what we're doing at first, like this first loop, is creating the desired prefix sum. So the array. So we're basically pushing back our last prefix value and then adding it to the current one. So like if the numbers were like 1, 100, and then 1000, we're doing that the current element equals the one we're reading. And so basically what we're doing is we're creating a prefix array and summing this element to the new one and then pushing it back in the array. So basically 0 is currently in the array. So we're reading that in and then summing it to the first number we read in, which is 1. So 0 plus 1 is 1. And then we read in another input, which will give us 100, and adding it to the current one index, which would give us 101. And then we're reading in the next element, so it's just 1000, and then we're adding it to nums of 2. So we should get 1000, like so. So basically, like that's the equivalent of what our for loop is doing, is creating our prefix array. Okay, once we have our prefix array built out, now we can actually take steps towards solving this. So let me just like draw an example of prefix sum array, like so. So basically, okay, it could look like this. And then what we're doing here is as I mentioned, it goes from r minus 1. We're not inclusive of the last element. So we're going to do nums of r minus 1 minus nums of L. So if I want to find the sum from from 2 to 4 of the original array non-inclusive of 4, then I'll just do 1 less than the index, and then the first index is just the normal index. So I read in each query q times, and then it takes a constant time processing, which is why this whole section takes like q time overall, and this takes n time. And I just print out the sum over that range by accessing the indices of our prefix array and doing it for each query. So after we do that, all that, we're done with the problem. We printed out the sum of every query we want. Okay, now for another problem.
Yeah, so let's take a look at this next problem over here. So I'll read the problem quick so you guys can kind of gauge the idea of what it's asking for, and then we'll go over the solution. So you've probably heard of the game rock, paper, scissors. The cows like to play a similar game they call hoop, paper, scissors. So the rules of hoop, paper, scissors are simple. Two cows play against each other, count to 3, and then simultaneously make a gesture that's hoof, paper, or scissors. Hoof beats scissors, scissors beats paper, and paper beats hoof. So if a cow makes the hoof gesture and the other one makes the paper one, then the second cow would win. Of course, it is also possible to tie if both cows make the same gesture. So Farmer John wants to play against his prize cow, Bessie, at end games of hoof, paper, scissors. And since Bessie's an expert of the game, she can predict each of Farmer John's gestures. Unfortunately, Bessie, being a cow, is also really lazy, so she tends to play the same gesture multiple times in a row. In fact, she's only willing to switch gestures at most once throughout her entire set of games. So this is the kind of important information that you have to keep in mind for this problem. So for example, she might play hoof for the first X games and then switch to paper for the remaining N minus X games, right? So there are a total of N games here being played. And given the sequence of gestures, Farmer John will be playing, please determine the maximum number of games that Bessie will win. So first, we're given the input of how many games there are. So in this case, there's 5. And then it tells you each turn, like this is turn 1, game 1, game 2, etc., all the way to game 5. It's going to tell you what Farmer John is playing in each game. So let's observe how to do this. So let's say just visually looking at it, we can see that there's 2 P's here and there's 1 P here. So if Farmer John kept if not Farmer John, sorry, since Farmer John is playing P 3 times, he could play whatever beats paper, which is scissors. So basically Bessie could play scissors 3 times, and he could also switch it to over here. Since these are scissors, we need to play hoof. So Bessie could switch his hand 1 time to hoof. Because as stated in the problem, remember that Bessie's only to switch hands at 1 time. Let me find it. She's only willing to switch gestures 1 time throughout the entire set of games. So she could put her switch over here and change the hoof, and she would be able to win 1 more game with that. So she would win a total of 4 total games, which is the maximum number of games that she could win. So let's take a look at how this is connected to prefix sum. So yesterday we went over an example, if you guys remember breed counting, where we have different types of cows, and you have to print out the number of cows in a certain interval for each different type of cow, right? So we had to maintain 3 different vectors for that because they're all different breeds. So similarly, we're going to apply that kind of concept over here. So we can see that there are 3 different move sets. So we want to count the number of P's, H's, and S's in a certain range, right? So that's kind of the hint that I'm going to give you guys for prefix sums. So I'm going to say something like P is equal to, so I have to start off with 0. Remember, that's a placeholder. Then there's 5 games total. So I'm just going to write the indexes up top here. So how many P's are there at each interval? So there's 1 P here. Sorry, I should write the number. 1 here. Then it's going to go up to 2. Then the third game, there's no P being played, so it's just going to stay at 2. This is a prefix array, by the way. So then we're going to build it up because there's another P here. And lastly, it'll just be 3, right? Then we're going to do the exact same thing, but with H and S. So we're going to build our prefix array here. So start off with a 0 placeholder. And we only see 1 H, which is over here. So it's going to be at the third game. So 0, 0, 1, 1, and 1, right? And finally, we're going to have S. So this is only played the last point of the game. So we're just going to have zeros all the way until the last element. So here is the idea. These are the end games that are being played. She can only switch hands one time throughout the entire course of all these games. So let's say she switches hands at this point, right? So she plays the same hand before this point, and she plays the same hand, she switches and she plays the same hand for the remaining games. Well, the prefix array has essentially solved what we need to do. We already know how many games she needs to win by just getting the range of the amount of games she would win inside that amount of games that she can win during that interval, right? So over here, let's say that how many wins can she get if she played P for the first 2 games, right? That's the amount of P's being played because Bessie can play whatever she wants, right? We don't really care what Bessie plays as long as like she can win the game, let's just say. Since she knows what Farmer John's going to play, just assume that Bessie is able to win every single game that she plays. So with that assumption in mind, we're going to look at this and we're going to say, okay, so if Farmer John is playing P 2 times, which stands for paper, then we're just going to assume that Bessie is going to play scissors that entire time. And she's going to win every game in that range. So if she's going to win every game in that range, she's going to get 2 minus 0, right? We want the entire interval, right? So let's do like another example of like how many games she would win in a certain range. So let me erase all of this. Okay, so let's say that she is playing P, or no, let's say she's playing H, okay? Let's say she's playing H between games 2 and 4. And we want to determine how many games she would win between games 2 and 4 by only playing hoof. You would just have to take 1 minus 0 using the prefix sum formula, right? Prefix of B minus prefix of A minus 1. So this would be A and this would be B. So prefix of B, I'll just use a different color here. So prefix of B minus prefix of A minus 1, right? That's going to be the amount of wins that you get in that range of games that she's doing if she plays hoof, right? So that's the amount of, so basically what we've been able to determine is the amount of games that Bessie can win in a certain range by playing a specific hand, either paper, hoof, or scissors. So that's going to give us the amount of games that she can win, but we want to be able to maximize the number of games she plays, right? So obviously we could see that if she plays paper over this range over here, and she plays scissors over here, right? The scissors being played at that last point. So like basically again, like let's just assume that we can win any matchup that we're against. If she plays like whatever counters scissors at the last point in time over here, then she can also win a game, right? Whatever counters scissors, she can take the last win from over here. So what's gonna happen? Let me erase this quick. So like just like from what we described earlier, I'll circle it again. So we're talking about how she could play whatever counters paper for the first 4 rounds, and she'd win 3 of those rounds total, right? Because she has 3 P's over here, so whatever counters P will be able to give her a win. So she'll get 3 wins from playing whatever counters P. She'll switch her hand right before she gets to S, and she'll be able to play whatever counters S and get 1 more win. So total, these will be 4, and that's her answer right here. So the idea for this specific sample input inside this prefix array is we're going to play up to the 4th game, and between games 1 and 4, we're going to win a total of 3 games, right? 3 over here. And the way we see that is this is A and this is B. So the amount of games she would win between that range is prefix of B, which is 3, minus prefix of A minus 1, which is 0, right? This is A, so A minus 1 is 0. So 3 minus 0 is equal to 3. So we're going to add that and then to our answer. And then we're going to take whatever counters S, 1, and we're going to subtract A minus 1. So since she switched hands right here, right? She switched hands at B. And that means that that's where we need to, that's our A minus 1. So this is our new B, and this is going to be our A minus 1, right? And then we're going to take that, we're going to say 1 minus 0, and that's equal to 1. So now we got our 3 and our 1, and we just add them together to get 4. So that's the idea behind this problem, but how are we exactly going to approach that when we're writing our code? Well, there's several possibilities, right? It's not always the case that we want to switch our hands at the last possible moment. These letters could be in any order. So the way we want to see how many maximum wins we can get is we're going to keep a running variable like we've been doing. Often when you see like maximum number of something, you want to keep like a running variable. Not always, but oftentimes when you see a maximum or minimum, you want to keep a running variable. So we'll just say wins equals 0. This is an integer, by the way. Integer wins equals 0 or something like that. And then so we'll loop through every interval and we'll check how many wins she can get by playing a certain interval. So let me describe what that means. So I'm going to check this range. Sorry, I'm going to check this range. She only plays whatever counters paper first, and then I'm going to check this range because she can only switch hands one time, right? So that's why I'm only having 2 boxes to separate it. I'm going to play whatever counters paper, and then I'm going to switch my hand. I'm going to play whatever counters hoof for the rest of the game. I'm going to check that and update the amount of wins I would get. And then I'm going to do the same thing with comparing P and S. I'm going to play P only, and then I'm going to check S. How many wins would I get total? If I played whatever counters paper, I switch my hand and play whatever counters scissors for the rest of the game. So I'm going to check that, and then I'm going to continue. So that's the case if I play hoof one time. If I play paper one time. Let's say I played paper 2 times. Then I am going to, let me redraw that box. If I play paper 2 times, then I can play whatever counters hoof for the rest of the game, whatever counters scissors for the rest of the game. And I'm just going to keep track of how many wins I'm getting by adding them up. And I'm just going to update this wins counter each time until I get to my answer. So that's kind of the solution that we're going to use for this problem. So let's move on to the code. Okay, so like I said, generate a prefix sum of the hoofs, papers, and scissors being played, loop through the combinations of them, and generate the maximum number of winning combinations, right? That's essentially what our algorithm is. So standard file IO, and we're going to create our 3 vectors of H, P, and S. And we're just going to read in the input at each point, and if it's like a P, then we're going to add it to the prefix sum, et cetera, right? We're just going to get the prefix array for H, P, and S. This is pretty standard. And then we're going to initially set solution equals 0. So this is just basically like integer wins equals 0, right? What I said in the last slide. So here we're going to loop through every combination. So like, let's say H is equal to, I'm just going to draw this out. I won't write all the numbers again, but yeah, here. So I'm going to just create like an anonymous function. You guys haven't learned this, but you guys also could just make a function over here. But I just was lazy and I just made a function here. It's called a lambda function if you guys want to know more about it. But basically, you guys don't really need to know this. You can just make like a variable, make a function up there, and then just that does the exact same thing. And it's going to take in 2 vectors as input. And it's going to update the solution to the maximum of what it is, because we want the maximum number of wins, right? And it's also going to take in the range of the range of everything that we can get, right? So let me draw this out again. So H, P, and S, right? These are the 3 types of plays that we can play. So let's say that we are at index I. Let's say I is over here. Then we want to take the maximum. We want to take the number of wins that we get from here for H and add it to P, the amount of wins that we get from I to N, right? So essentially, if we want to get the sum of the number of wins from each of these ranges, we're going to take the number of wins that we get from A at index I, and we're going to add it to the prefix sum of P. So the prefix sum of P is going to be the B of N, right? Minus B of I minus 1. But it doesn't matter because like we're just using different indexing. But yeah, we're just going to subtract B of I minus 1 to get the amount of wins inside this range over here. So that's what this code is doing over here. It's comparing 2 vectors, and it's getting the maximum of the solution and the amount of wins that we could potentially get by using 2 different combinations of switching hands, right? Because you can only switch your hand one time. That means you can only play 2 different things, A and B, right? So then I'm just going to call this function all the possible combinations. So if I have H, P, and S again, I'm going to see the combinations of, do I want to use H over here and P over here? Or do I want to use H over here and S over here? Do I want to use P over here and S over here, et cetera, right? I'm checking all possible different I'm just checking all the possibilities of what I want to update. And notice that even though I say all possible, it's really only calling this function in constant time. It's not really doing like a for loop or extra work or anything, because we have a prefix array generated, which gives us the amount of wins that you would get in a certain range that you could like basically counter each type of play of Farmer John's, right? So we're going to update the amount of basically wins that you can get maximum, and we're just going to print out the solution. So yeah, that's the idea behind this problem. Let me know if you guys have questions.
Okay, if there are no questions, we'll talk about binary search, which is today's algorithm. Okay, binary search is a very efficient log n time solution or algorithm to a problem at hand, and the array must be sorted to use this algorithm. And basically what the purpose of binary search is, if you want to find a specific element in a sorted array, you can use binary search to find it very fast. And it removes half the search space in each iteration. So basically what I mean by this, let's say in this array, my target is 7. And then in terms of binary search, what it would do, it would have a pointer at the 2 ends, and then it'll check the middle element, which is this one. Is the desired element greater? Is it less than 6? No, it's not. Is it greater than 6? Yes, it is. So we're going to check the upper bound now. We're going to remove this part of the solution space, and we're going to move our pointer here to 1 plus the mid. Now we're going to check the middle. Is the desired solution less or equal to, or is it greater than? It's not greater than 8, and it's less than. So we're going to move the pointer down, and now our low and high point the same place, and the mid is equal to 7. So our answer is 7. And as you can see, we did 1 divide, and then we cut the solution space by half. Then we cut it again, and then we found it. So basically on this array of size 7, we only took 3 operations, or actually 2 divides to find it. And as you'll see, for very large operations, it'll only take very few times because you're dividing it in half every time. So as you can imagine, that's very quick. You're going from like an array of size n to an array of size n over 2 to an array of size n over 4. Basically, as you're searching for this, you can think of it that way. And the amount of operations you're doing here is log n. So yeah, basically we're running in terms of log n time, which is way faster than the normal thing you would do, which is just search every element in the space until you find it, which would take, that would be n time complexity.
So I also want to mention, so there's like a saying that if you guys have like a dictionary or something, you can find any word in the dictionary by turning at most 10 pages. So that's kind of through binary search. So I'll give you an example. So you know that dictionaries are sorted in alphabetical order, right? So that's why these are kind of sorted and you can apply binary search. So normally if you have a dictionary with, let's say, like 1,000 pages, I don't want to, like, let's say the word was all the way over here, like 987 or something, right? I wouldn't want to go through one by one, loop through this entire dictionary and find the word by going there, right? That's not efficient because then I have to perform 987 operations, which sounds pretty horrible for just page turning for a word, right? For a single word. So whereas binary search, I can tell. So let's say my word started with like U, right? It might like be somewhere around 987. The page number out of 1,000, let's say there are 1,000 pages, then like all I have to do is check the middle. is my word over here, does it have a greater alphabet letter or a lower alphabet letter? Well, since I know U comes after the middle of the alphabet, I can just discard this entire array. I don't have to even consider it at all, right? So that's why I'm saving a lot of time by cutting the amount of pages I have to go through. So then I'm going to check this range over here. I'm going to look at the middle and say, is U after this or before this? Well, it's after this. So again, I'm cutting a significant amount of pages I have to go through. And it's going to continue doing this until I'm able to basically narrow it down to a single value. So that's why binary search is so efficient. It doesn't have to go through everything, all the possibilities. It just finds it as soon as possible by cutting through the solution space.
Yep. Also, I'm just gonna open up a graph to show you guys what the difference in efficiency is between the normal searching with iteration and then the binary search. So the x-axis
Put
is
log base 2.
log base 2.
Yeah.
I mean, like the base doesn't really matter.
I mean, it doesn't really matter. Just underscore 2. Yeah.
Yeah. Okay. Sure, I guess. Okay, so in terms of this, you can see that the log graph. Okay, let me just explain what the axes are. If you didn't know. So x is the size of the inputs and y is the time of how long it'll take to run. So as you can see, as your input becomes really large, log starts to look like, it almost just looks like a line once you just like extend it out because it's really efficient. But your n time complexity will keep growing at a very at a constant rate, but it's going to like it'll grow at a constant rate, but it's much larger than the log graph. And as you can see at if your time, I mentioned that the USACO limits was 5 times 10 to the 8th. So at 5 times 10 to the 8th, look how many operations your O of n you're like if you had a 5 times 10 to the 8th input, then your output would be 5 times 10 to the 8th, the amount of operations you're doing. However, the amount of operations you're doing for just a binary search algorithm is significantly less, like it's almost negligible. Probably like around like, if I had to guess, it's maybe like 50 or like probably even less, probably less than that. So like, yeah, it's you really want to, if you're using binary search, you know you can do, even if they give you like input size of like 10 to 30 or something like that, like you can be confident that binary search might be this algorithm you're looking for if they give you really large inputs because of its efficiency. Okay, let's move on to a problem relating to binary search. So before we go into binary search, I want to go over the iterative or naive way to do this. So given a sorted array of numbers, return true if x exists inside the array and false otherwise. So how we would normally do this is we would iterate through the entire array. And if we find a number that equals the desired number we're looking for, we return true. But if we iterate through the entire thing and don't find it, we'll just return false. And this is the O of n solution, which is the solution I showed you did not it did not grow or scale as well as the log n solution, at least from Desmos charts, the number of operations that has to do. So significantly faster way to do this is using a binary search algorithm. And linear time, as I said, it doesn't scale well, so it could be slow for very large answer input size. So in terms of binary search, what we're doing here, I can bring back an array that I've drawn where. Okay, so 1, 2, 3, 5, 6, and I'll just put a 7 here. Okay, so now what I'm doing is I'm setting the low pointer here and the high pointer to the last element to start off. And while low is less than high, so if low ever equals high or like any or is less than high, then we know we have to stop. Okay, so we're determining the mid, which is 4. If we determine that the mid is the desired number, let's say my desired number is 3 in this case, just to like not make it super easy. Okay, so then if it's equal, return true. It's not. Okay, is our solution the number that we're looking for? Is it is our current number less than the number we're looking for? No, it's not. And then the number that we're looking for is actually less than our current mid. So we'll go into here. The high will equal the mid. So now our new high becomes this element right here. Okay, so now we're going to repeat this process. We're going to find the mid, which will be this element right here. Is our desired number greater? Yes, it is. The mid is actually greater than our current element. So we're gonna increase our low to account for that. So now we're gonna move our low up here, and then we're gonna run the operation again. And then if we take mid of this now, it'll, since there's only returns integers, we'll do 3 plus 4 divided by 2, which will return this. Is our mid equal to x? Yes, it is. So we'll return true, just like that. That's pretty much how this algorithm, this code is working on the actual array. It's basically just dividing the solution space until we find our answer. Okay, so some tips for solving binary search problems. Sometimes you need to, okay, so first we need to find out what exactly you're binary searching on, what is the content of the array, and what are we looking for. Some problems that state the terms like maximum, find the minimum, is where it will be useful. So one specific example is if I had an array of like booleans, and if my if I'm currently if like I've let's say like each element represents, so like 1, 2, 3, 4. Okay, so like if with the current number of cows I will be able to fit them in a pasture. For example, that's what the problem is. So if I have 1 cow, I can fit it. If I have 2, I can fit it. 3, I can fit it. 4, I can fit it. But once it turns to 5, I can't fit it anymore. So basically how binary search would help this is I would use it to find the space where true switches to false. So in this case, let's say the problem asks for what's the maximum number of cows you can use to what's the maximum number of cows you can fit in the stall. Then I would do binary search and run it. Okay, if it's in the middle, I would look for the first false element, for example. So, or I could look for the latest true element. But let me just go to the middle, and then let's say I'm looking for the smallest false element. So since it's not false, I'll want to search ahead, and then since I'm comparing it, and now I change the bounds to here, and then this is the mid. If the mid is false, then I want to move it down because there could be a smaller false. There could be like a smaller false, which would be better than the current one. So then I'll go here, and since my low and high are equal to each other, then that means that I found the smallest false, and this value represents the first value that I can't fit all my cows in the pasture. But if we want to return the maximum, then I would just do like 1 minus this value, and then I could find this, which is the first true value that I would want. And there's many ways I could have solved this problem. I could have found the highest true instead of the lowest false. That would be another way. But yeah, as you can see, I used binary search to find the maximum number of cows I could fit into my pasture on this Boolean array. So that's one example. And also, given an array of numbers in an integer x, find the first number greater than or equal to x in the array, or return -1 if it doesn't exist. Okay, what this is essentially doing is, if my current number is greater or equal to the one I want, then I want to search the smaller solution space. Otherwise, I'll search up. And then, okay, so I have an array of numbers, and then like, let me just, okay. 1, 2, 3, 4, 5, 6. Let's say my integer is 2. Okay, I want to find the first number that's greater than or equal to. So how I'm going to do this is I'll keep on going until my low pointer is greater or equal to the high pointer. So this is basically just what I've been doing the whole time, but I'll show it again. So mid pointer is here. And since this is greater or equal to the number that we're looking for, which I'm just going to set to 2, then I'm going to set high equal to mid. So now my new high is here. Then I'll search the middle. And since it's greater or equal to, I'll set the high equal to the mid. And the answer is equal to the min of the current answer and then and the current element. So now the answer is 2, which was the previous mid, and now the new mid is 1. But then 1 is not less or equal to. So now I'll boost up the low to equal mid plus 1. And now they're in the same position. So I'm going to break. So I determined that the lowest number that's greater or equal to the element I'm looking for is 2, which is in that index that they're pointing at. So I just print out the answer. And what it's just doing here, if it never found it, like if low just became greater or equal to high, but I never found the answer I was looking for, then I'll just return -1 because it'll just stay the same. The value will not have changed. Otherwise, I return the answer, which is the number I'm looking for. Okay, so now we'll do some examples in binary search.
All right, so let's take a look at our first example here. So this is academia. I'll let you guys have a few moments to read this problem and then we'll go over the solution. 10:40 right now, so let's spend 5 minutes. About it's a pretty long problem, so I'll give you guys some more time to read that. It's been about 5 minutes, so let's quickly go over the solution. So read the poem first. So she's basically, I'll just go over it quick. So she's had N papers. Bessie has published N papers. Is less than 10 to the fifth. And each paper has a certain amount of citations, also less than 10 to the fifth from other papers. She hears about the H index, which is how they're going to measure how successful a paper is. And H index, the largest number such that the researcher has at least H papers with at least H citations. So for example, if she has 4 papers and the amount of citations that each paper has is 1, 100, 2, and 3, then the H index is 2 because there's one citation, sorry, let me see this again. Largest number H is at least H papers with at least H citations. So our largest H index is 2 over here because we have at least 2 papers. So we have 3 papers, in fact, but we need at least 2 to have at least 2 citations or more. So this has 2 citations or more, this has 2 citations or more, and so does the 100. So if we try to say that each index is 3, well, we only have 2 total papers that fit that, which is not going to fit the requirement for the H index, right? So over here, you can see that if the H index is 3, then we have 3 papers over here that are at least 3. So that's why the H index is 3 there. We can't do 4, obviously, because there's only one paper that's greater than 4 for the amount of citations. So to up her H index, Bessie is planning to write up to K survey articles, each citing many of her past papers. But due to page limits, she can only cite at most L papers in each survey. So there's she can't cite the same paper multiple times. And here she says, wait, you're opening up the console. Yeah, okay. So I'll just read this again. To upper H index, Bessie's planning to write up to K survey articles, each citing in many of her past papers. However, due to page limits, she can only cite at most L papers in each survey. Of course, no paper may be cited multiple times in a single survey, but a paper may be cited in several surveys. Okay, so determine the maximum H index she may achieve after writing these articles. Bessie is not allowed to cite a survey from one of her surveys. Note that Bessie, okay, like this part doesn't really matter, but yeah, for this problem. So essentially for the sample input, what we're given is N, K and L, like the inputs that it gives us. So it gives us the amount of papers there are, the amount of survey articles that she can write, and the amount of time she can change these survey articles over here. Cite and most L papers in each survey. This is the amount of papers that she can cite, right? So here we want to determine the maximum H index. So like we said in the previous slide, often when you see the words maximum or minimum, something like finding the max or minimum, not always, but very often, you can think about binary search as a possible solution to this problem, because you want to find, like, let's say this is our like Boolean array here. So this would work, this would work, this would work, this would work, and then finally these would not work. So you would test to find the last true or the latest or the earliest false, and then subtract 1, and you would find the first true, like the latest true that you can have that still fits a solution that could be your maximum, right? So we want to think about binary search here. So it's asking us, it gives us these papers in the first input. So let's take a look at that. So in this input, I'm going to sort this to kind of make this easier to look at. And you can see that currently the H index is only like 1, right? Because we only have one paper that is at least 1. If we say 2, then we don't have 2 or more papers that are greater than 2, right? We only have the 100 that's greater than 2, but we don't have another value that's greater than equal to 2. So here we have those 4 survey articles, and she cites each paper 1 time, writing 4 survey articles. Then she can cite each, if she cites each of her first and third papers twice, she will then upper index by 3. So if she basically cites the papers each time once, K survey articles, right? And she's going to do this. So she's going to say 2, 2, 2, and 100. And then she's going to up it by 3 again. She cites each of her first and third articles once. Oh, sorry, twice. She cites each of her first and third articles twice. So over here and over here, then her H index will be 3. Okay, so what she wants to do is 100. She wants us to up this by 2 and up this by 2. So this becomes 3, 3, 1, 100. So that we have at least 3 articles that are at least 3, right? So that's going to be our H index. That's the maximum she can bring it up to. And this input over here, 414, let's just sort this again. She can cite at most 1 article total. So this is the amount of articles that she can cite total. But she can't cite like 2 articles here because K is only equal to 1. So she can only cite like 1 total article, right? So she can only do it to 1 article, but here we had 4, so we can do it to as many as we want, right? And if Bessie does any of her papers by upping it by 4, then she'll succeed in getting the H index to be at least 2, right? If she bumps this up or bumps this up or bumps this up, her H index will be at least 2. So let's look at our solution here using binary search. So the key idea to remember in this problem is to read in the papers and sort them because it's going to make it convenient for us to look through. And then we're going to apply binary search in the H index. Always think about like what you want to apply binary search to, like what's the object that you're trying to binary search on. So in this case, it's the H index, right? Because we want to find the maximum H index that we can achieve. So we want to binary search on that maximum H index to kind of quickly go through the possibilities of H indexes and see if they work. So again, you just have to check if they work or not. If they work, then you just have to continue looking for the maximum answer. So we're going to read in our input. So I'm using LL equals long. So because the numbers can get pretty big sometimes. Longs, like we introduced in our first lecture of the bootcamp, are like kind of integers, but they're bigger size because integers go from -2 to the power of 31 to 2 to the power of 31 minus 1. If the number is bigger than this range, then outside this range, then integers won't work anymore. So that's why I'm just using long to kind of make it convenient, but it has the same functionality as an integer. So I'm going to read in as input. I'm going to read in the papers as input, like what they said, right? And then I'm going to sort it. So then I'm going to set a variable to be the size of the papers. And I'm going to binary search through this. So this is a pretty standard like binary search setup. So I'm going to set low equals 1 and high equals like anything you want. This is our solution space. So 1 to like whatever the number is over here, right? And we want to search through solution space for the H index. So this is the H index, the maximum H index that we can print out for any case is within this range. And I'm going to say while low is less than or equal to high, while I haven't found my answer, I'm going to set the mid equal to low plus high divided by 2, right? And then I'm going to make my vector of the papers. And I'm going to check if it's possible for this H index to exist. If it's possible, then that means I can continue looking for a maximum H index. So I'm going to say low is equal to mid plus 1. Otherwise, I know that this H index specifically will work. So I'm going to say high is equal to mid minus 1, right? And eventually, when low is less than or equal to high, when this condition becomes false, then I'm going to just print out the maximum H index that I was able to achieve. So the way we're going to check if each H index was possible is through a Boolean function, a function that returns a Boolean that returns true if it works and returns false if it doesn't work. So the maximum difference and operations needed, I'm going to set as 0. So remember that each, it gives us K and L, the amount of articles that we can cite total and the amount of times we can cite each article, right? So the total number of citations I can create in total is K times L, right? So that's kind of some intuition that you guys need. And the maximum difference to be 0. So we're going to loop through the papers here. And we're only going to want to switch papers that are less than the H index, right? We don't want to switch numbers greater than the current H index. That wouldn't make sense, right? And we're going to take the maximum difference and we want to check if we can bring that paper up, right? So we have like 1, let's say 2 actually, and 100. Or like, let's just use the other example that they used. So 1, 2, 3, 100. And I want to check if I can bring the H index up to 5, right? And let's say K is equal to like 2 and L is equal to 2. Well, this is the amount of papers I can cite total. And this is the amount of times I can cite each paper, right? So I'm going to loop through and I don't want to increment this value, right? It doesn't make sense for me to cite the 100 because it's already contributing to the H index. I don't want to continue contributing it. I want it to maximize the possibility that I can up my H index, which means I need to up the lower ones. I need to increment, like I need to cite the papers that are at the lower end of the spectrum, right? So I only want to check the ones that are less than the current H index. And I'm going to get the maximum difference. So let's say like 1 is over here, and the H index minus P, basically the H index minus the current paper. I want to check like, can I increment the value? If I want to check if I can get the value to 5, if I can get the H index to 5 in this case, then I need to check 5 minus the current paper minus 1 is equal to 4, right? I need to check if this 4 can be basically achieved with this combination of K and L values. And obviously you can see that it's not, because I can only cite 2 papers, that's fine, but I can only cite each one 2 times. If I bring this up 2 times, I can only bring it up to 3, but I can't bring it up to 4 over here, right? It won't reach that H index. So I need to keep track of the difference of the papers and the H index, and I need to keep track of the amount of operations I'm doing. Remember that I'm limited to K times L operations. So I'm going to check if the maximum difference is greater than K, that means we can't do it. And if the amount of operations exceeds K times L, I also can't perform this. I can't get all my papers to its H index. I'm going to return false. And I'm going to write the same code over here, return false if that possibility is not possible, and otherwise return true. So then I'm going to know that this possibility of this H index works, and we can continue looking for other H indexes. So we're able to quickly look through the H index and basically calculate if each one is going to be a possibility or not with binary search. So we're going to quickly look through the possibilities of H indexes and just print out the maximum at the end. So that's what the idea is for this problem. So let's take a look at our second problem here. So I'll just explain this quick for this problem. So it's wormhole sort. This is a pretty challenging solver problem, as you guys will see in the code. So it goes as n cows over here, n and m. And it's going to basically tell us that, okay, these are the positions of the cows. And let's see, there are these connections between the cows, and basically the wormhole size between them is like, I'll give this as an example, 3, 2, 1, 4, right? So we want to sort these cows back in order into 1, 2, 3, 4. And to do so, you have to like switch pairs of cows, but switch like there's basically a hole that connects 2 cows, right? In this problem, it's telling us that there's a hole between 2 cows, and the size of that hole is like a certain number. And it's telling us what is the maximum minimal wormhole, like what's the minimal size wormhole that I need to put a cow to switch through in order to get this sorted order. That's basically what the problem is asking. So let's just look at this quick. So 4, 4, 3, 2, 1, 9. So between 1 and 2, the size is 9 over here, right? So basically the wormhole size between here is 9. So if I wanted to switch these 2 cows, it's going to take like a width of 9. If I want to switch 1 and 3, it's going to take 7. And if I want to switch 2 and 3, it's going to take 10. And 2 and 4, it's going to be 3. So I want to basically get the minimal wormhole length that I can travel through and still be able to get 3, 2, 1, 4 and change it into 1, 2, 3, 4. So just looking at this problem again, you can see the word maximal minimal. Basically, if you see max or min again, you can often think about binary search to approach the problem. So the maximal minimal wormhole width, it's just telling you what you want to binary search on, right? Well, you want to binary search on the wormhole width, right? So notice how over here we have 3, 2, 1, 4. If we want to switch it to 1, 2, 3, 4, we need to look at the cows that still need to be swapped. Essentially, we need to switch the 3 to here, and we need to switch the 1 to here. The 2 and the 4 are already sorted in their proper order. So we need to see if there's a way for 3 and 1 and over here and over here to be part of the same component, because if they're part of the same component, they can basically switch with each other, right? So we can think about this as graphs again. This is a clue. Over here again, bidirectionally, if you guys remember when we were covering DFS, it was that we can basically see the word bidirectionally, location A and B, as kind of like the clue that we can use a graph in the problem. So over here, we can see that we're combining the elements of a graph and binary search with the maximal minimal, right? That's how we're getting the clue of what kind of algorithms that we're going to use in this problem. So we want to switch 3, 2, 1, 4 into 1, 2, 3, 4. We want to turn this into this through the connections that gives us. So we need to check if there is a way for wormhole one to reach wormhole three eventually through like any type of combination of switching. So it doesn't matter how many times you switch it or like what's the order we switch it in, as long as we have the minimal wormhole length that does so, then we can print out that as valid. So let's look at the code over here to get a better idea of what I'm saying. So as you can see, it's pretty messy, so I'll go over it. So let's take a look at our main function first. That's where we're going to mainly be working. So I'm going to read in N and M, and I'm going to read in the positions that it's giving us. This is the starting position of each cow. Okay, so then I'm going to have a set over here that contains the differences, and it's basically going to contain what's not sorted. So for example, 3, 2, 1, 4, and 1, 2, 3, 4, and I'm going to contain everything that is not sorted. I'm going to push it into this set over here because that's what we need to end up being able to swap, right? I'm going to say if differences.size equals 0, that means that not everything was sorted already. So we don't need to do anything. And as the problem states earlier, if you guys saw, it just asked to print -1 if there's nothing that needs to be sorted. So if the differences.size equals 0, we're done. Otherwise, we have to do this. We have to construct a graph, and it's going to tell us for each like connection, it's going to tell us what wormhole it connects. And then it's going to tell us what's the wormhole size. So I'm going to store that with a pair over here, BW. So a graph at index A is going to connect node B with the size of index W. So I guess you can think about this as an edge, right? So if you have like a node over here, node A and node B, the wormhole size can be like W, what is like necessary to go between them. So this is kind of the concept of edges that we went through for graphs. And we're going to push back the weights over here again into just like a separate vector to store it. And then we're going to sort the weights in order. Then we're going to start binary searching. We want to binary search if each possible weight is like the maximal amount of like basically the maximal weight that we can still have while we're still moving, being able to sort the array, right? So I've created a sorted array of weights. I want to check if what's the maximal weight I want to be able to use. Should I cut it off here? Should I cut it off here? Should I cut it off here? If I have the weight to be this value, can I get the cows to be sorted in order? If not, then I have to continue increasing the weight size, right, to over here. Can this weight size allow me to still sort the cows in order? So that's what I'm doing. I'm binary searching through the different weights, and I'm going to print it out at the end. So if I want to check if each weight is possible, then I need to be able to add 2 parameters, weights, check the weight that we're currently at and see if it's possible by looking at differences and seeing if the differences can be still like solved and be able to be like bring the cows back to sorted order. So if I want to check if this is possible, I need to DFS. I need to check if I can be able to access every single node that I want to. Because, for example, if I had 3, 2, 1, and 4, if I find out that 3, 2, 1 can all switch between each other, then I don't care because I can just get 1, 2, 3, and 4. I don't care how many swaps I have to do or what combination of swaps I can do. If I find out that 3, 2, and 1 are part of the same component in the graph, then I'm going to be able to sort them no matter what, because I can just swap the values infinitely as needed. So, of course, I want to check the edge restriction. There's basically this is the maximum weight that we can travel through, right? So this is the edge restriction. This is the maximum wormhole size that we can travel through. And we're going to call DFS on this. In our DFS function, we're going to you can see that there's literally the same DFS function as we've been using the entire time, just a little bit modified for this problem. We're going to set visited starting node equals true, insert the starting node, like this is the place that we've been visiting. And we're going to look through every node over here. And if we haven't visited and the edge limit is able to be fixed, then we can DFS it. And we're going to find out basically the entire component of nodes that are connected here and be able to basically see if we can swap the nodes together. So if we have our visited nodes, which is included in the must visit set over here. So basically, if the nodes that we visited with a DFS function are able to fit through the must visit, then we're going to return true. Otherwise, we're going to return false. So this is basically going to get the maximum weight for us because our DFS is going to consider the edge restriction. Our binary search is going to find the maximum weight that we can go through, and we're just checking if that weight is possible using DFS. So that's the idea. The key idea is to notice that we need to apply DFS and binary search and just simulate for each wormhole size that we're binary searching if the size works or not. So that's the idea behind this problem.
Okay, then that's it for this lesson, and that's also it for the entire course. I know many of you guys are going to MSJ next year, so look forward to seeing you then. If you guys are approaching MSJ level next year. And yeah, if there's no questions, then that'll be it.
Yeah,
So,
thank you everyone for coming to attending our boot camp. We really appreciate everyone here and supporting us. We hope you guys learned some important algorithms over here, and you guys can kind of start your competitive programming journey, get a better idea of like where to start. You can always reference our slides posted on Google Classroom if you need help. And yeah, that's basically it. Thank you, everyone.
yeah. See you.
Thank you.